Thanks for joining the ESIP ITNI and CDI Tech Stack Working Group monthly event. Today, we're really happy to be hosting Jake Gearon, who is going to be presenting on an open source workflow that he's developed and a Python toolset for quantifying lacustrine sedimentation using publicly available data. Let's go on to the next slide. Just a quick intro for Jake. So Jake is a 2020 ESIP grant recipient, and he received the award that helped to fund the project that he's presenting on while he was a master's student at University of Texas at Austin. He has recently moved to Indiana, where he'll be pursuing a PhD at Indiana University. We're really excited to see the results of the work that ESIP helped to fund in small part. And I'm really excited at both the workflow and tech stack that Jake has put together, as well as the way that he's aggregated publicly available data using an AWS API framework. And there's just a bunch of parts in there that I think a lot of us are really intrigued by, and we're really excited to see the demonstration and the product that Jake has. With that, Jake, I'll let you take over the screen presentation, and you're off and running.
Okay, great. Thanks, Eric, so much. Let me try and make this Zoom magic work. I think that's the wrong screen. Hold on. Share. Okay, do y'all see a Jupyter notebook, or do you see the presentation?
See the presentation.
Oh, you do. Oh, cool. Zoom's just being weird to me, I guess. Okay, but you see the full screen, not the presentation view.
Correct.
Okay, awesome. All right, everyone. Well, good afternoon. As Eric just said, my name is Jake Gearon, and I'm thrilled to be giving the webinar today for both the ESIP and USGS technical communities. Let me do it properly. The ESIP ITNI and the CDI Tech Stack Working Group. So I'm going to talk today about LakePy. So it's a Python package I and others developed with funding from the ESIP 2020 Winter Grant. So we'll get into the details in a second, but it basically serves as a Python package for accessing lake-level time series data, and is further equipped with several easy-to-use methods and metadata attributes for researchers, locals officials, or people interested in kind of monitoring water resources. Okay, so about me, let me get my little laser pointer rocking. Yeah, so about me, I'm originally from Maryland in the DC area, where I know some of you are based in, or at least Derek. But I moved to Austin, Texas for my undergrad, and ended up staying for my master's degree. So I just finished my master's degree up there in May. And that was specifically in sedimentology and stratigraphy, but I've always enjoyed coding and had some experience in my undergraduate with remote sensing coding. So kind of since then, I've tried to fuse sort of those research avenues, combining Earth surface processes, remote sensing, and large-scale data analytics. And so to that end, I'm starting my PhD in 4 days, actually. I just moved to Bloomington, Indiana, with Professor Doug Edmonds at Indiana University. So hopefully stay tuned for more of the similar stuff to come. Okay, so the project I'll be talking about today was pitched to ESIP during kind of the middle of the first year of my master's, as developing a lake level database for kind of global lake level data, and then proving it with a use case. So I'm going to be talking today kind of about the first part exclusively. So, in the title, when it says quantifying lacustrine sedimentation, we can talk about that at the end, but I think that everyone here is going to be interested in kind of the data architecture and stuff like that. So we're mainly going to be talking about the nitty-gritty technical stuff. So I served as PI on this project with help from my roommate at the time, actually, John Franey, who's studying carbon capture and storage at UT, but similarly had a yen for coding. So we're kind of coming into this as geoscientists first and kind of hobbyist coders, and I think this really helped us elevate our coding abilities into kind of development level coding, or at least I hope so. So the basic goals of the LakePy project are to gather existing lake level time series data from several open source databases, including the USGS NWIS. So then we host that data in a simple database, and relational database on AWS. We chose MySQL. And then attaching an API so that other researchers might have access without compromising the security of the database or without people having to go query SQL by themselves. And then the next and final step that we'll get into is a Python package that wraps around kind of that API interface. That just makes it easier and slick and yeah, hopefully easy for everyone. Okay, so the main problem that we're trying to solve is that there's a lot of people who are interested in stuff like lake levels, whether it's local people or just people, researchers, anyone interested in this kind of stuff. But if you get beyond just kind of looking at a picture of the lake water levels and you want to manipulate the data, the people who can like scrape data programmatically from the internet is like a lot smaller than the people that just want to look at the data or manipulate the data. So kind of the genesis of this comes from the beginning of my master's work at UT. I was looking at lake sedimentation in the ancient, actually, so millions of years of old rocks. But I was looking at modern processes as well to try and compare. And I found that I would often need to download time series of lake level data, and not just in the US, but sometimes in Tibet or sometimes in Australia or all over the world. And it was during this time I realized why so many data scientists say that 70% of their time is spent on some combination of data wrangling and data cleaning. I was spending a lot of time trying to figure out how to download the data programmatically with Python. Even when the data was readily available, operationalizing it quickly was never really an option. There was always some customized code I would have to write, even if it only took 5-10 minutes to kind of get it from data, sitting on a server in a text file to like a pandas data frame or something like that. So I figured it might be useful to have an open source, regularly updated database. It's free to access with basically Python 101 skills. And the more databases that get added, the more data that grows. And I guess it was kind of a lofty aspiration, but it also just seemed like a great beginning to an open source project. Okay, so why is something like this needed? Well, like I just said, obtaining time series data can take, no pun intended, time, or it can even be too technical for people without any programming background. I say this as someone that spent time in an academic geology department, and I can tell you this is like not an exaggeration whatsoever. I'm thinking of my undergraduate structural professor, a structural geology professor, who like would have no idea how to get data from the NWIS or something like that. And some of those people you'll never reach, but those that maybe just are taking an interest in Python or have an interest in the subject matter in lakes, could learn this pretty easily. And we decided to do this program in Python mainly because it's the language I'm most comfortable with. So for that reason, but also because happily it's becoming a mainstay in data analytics. And I wouldn't say it's quite beaten the R language to be the language of science, but I mean, it's coming there. It's getting there. Of course, R has some statistics stuff that Python can't do, but anyways. I mean, even at UT, when I was an undergrad, they rolled out a Python course, and it was so popular that they're requiring it now for undergraduates. And so, this is that kind of paradigm shift in computational literacy. That means that technical folk like us, kind of in this webinar, are going to be looked to in order to build out that data engineering architecture. And so I'm really hoping, I hoped and still hope that LakePy can kind of fall in that category of an open source project that takes data from available with effort to available with ease. Is kind of a snappy way, hopefully, to think about it. Okay, so let's get into it. So what databases are we pulling from, right? So initially we have to go and get a bunch of data to obviously host it in the database. So in the proposal, we kind of selected these 3 databases to build the prototype, which ended up being pretty comprehensive because they're good databases, 2 global databases and 1 national one. From left to right, we have Gearon with the Global Reservoirs and Lakes Monitor, which is a project out of the USDA's Foreign Agricultural Service. So they use a suite of satellites, including JSON, TopX, and kind of the ones that come after them, to regularly update global lake levels. And usually these only contain kind of the larger lakes around the world. The second one is HydroWeb, which is this French academic database that I think is a public-private partnership, although like some of the stuff is in French, so it's like I don't understand, but free to use, open source, with an account. And they use radar altimetry to resolve some lake heights around the world. They have some gaps in like places like Russia, which I won't touch, but other than that, pretty good. The last one is probably the most familiar to everyone here. It's the USGS National Water Information System. And this one was undoubtedly the largest database by far. It required more creative coding just because of the size of the data. And of course, the data goes back to like 1870 something, I think for the oldest stuff. So yeah, it's a lot bigger. But the thesis here is that lake level data is kind of scattered across these databases, right? So I wouldn't say scattered, but if you look in one and you're like, it doesn't have this random lake in Central Africa or something like that, then you have to go to another one. And it can take a lot of time. So that's what we're trying to solve and basically create that simple database that takes pertinent information from these databases and then houses it for public consumption. Okay, so this is kind of a schematic PowerPointy overview of how the LakePy ecosystem works. We'll get into the details kind of later, but starting on the top left, we have 3 databases which send data to the relational database hosted in Amazon Web Services. We just use, like I said, MySQL. I had no experience with AWS before this, so there's a lot of reading documentation. But after the data is in that database with a standardized schema, we have to make it accessible to people. And so we had to use AWS's API Gateway and their Lambda functions in order to kind of create an API that could be publicly accessible without compromising the security of the database. You don't want people just able to drop all the rows in your database or something like that. So that's kind of generally how it works. It goes from here. And then LakePy wraps around that API we built and then serves it to the end user through the Python package. So I'll walk through some of the logic of the 3 databases, just kind of an overview. I can always talk more about it. But this was the easiest database to scrape, Gearon, which is the Global Reservoir and Lakes Monitor. And what they do is they just host text files, right, on a server with kind of lake level information that's regularly updated. And then those files correspond to unique IDs that they give. And so we just took the master list of lakes and their IDs, which was provided to us by the Gearon team. And then just query and individually scrape the text files from the server, kind of get rid of the metadata, which kind of looks like this. Right, so if y'all have seen this before, you have this big metadata section, you have the column descriptions, and then you have the data itself without actually any column headers. And so something like this, right, I mean, it could be too technical for a lot of people. Maybe not for people here, it might be an annoying problem, but it wouldn't be a prohibitively annoying problem. But for a lot of people, this is just too much to kind of deal with something like this. And there could be a lot of people interested in Lake Michigan data. And I know there are dashboards and stuff like that for the Great Lakes, but for smaller lakes, that's not always the case. And that data is not always available for people to peruse themselves. But anyway, so we kind of take that data, put it into a 5-column format that I'll talk about, and then send it on to RDS with just simple like pandas to SQL, which is pretty easily built out. Okay, so HydroWeb provides access to their lake levels kind of similarly. So that, again, they just host it on a server, but they zip them, which again, I'm trying to show these things that like are maybe not too technically difficult to deal with, but could be, sorry, my cat got in my way, that aren't that hard to deal with, but could be the barrier to entry for a lot of people trying to look at 10 lakes or something like that. Decompress it, load it to Excel, save it as a CSV, convert it to a data frame. I mean, stuff to us that might be easy, but to them might not be. So I think, researchers, especially good researchers with great ideas on things like climate change or water resources, shouldn't have to do this kind of pain in the butt stuff. We should leave that to people like us in the open source community or funded projects from public or private sector. Okay, so now we get to the NWIS. So the NWIS is fantastic. It's used by almost every like sedimentologist I know, at least that work on active processes. But it was the biggest by an order of magnitude, and that comes with data implications. And also the USGS is just old. It's an old institution. And so things like where there's 23 different water height parameters, where one is maybe the elevation of the reservoir surface above a datum in feet. And another one is the water depth from surface to bottom in meters, right? So it can be tricky to say, okay, what are all the sites in the NWIS with the lake identifier, and then basically figuring out every single water height parameter, scraping those, seeing which of those have daily values, and then sending them over to our MySQL database. And so that could take a few hours each time trying to pull all that data. I actually thought that I was worried that the web team was going to like flag my IP or something for like trying to like pull all this data all the time. But thankfully they didn't, and I've stopped querying their servers so much. So so sorry about that if anyone works there. But okay, so we set up the global lake level database, right? So all the data has been now taken from these three databases and scraped and turned into the proper columns and then sent to our database, which is a 2-table schema. So we call it the global lake level database, which is funny because it's just a little MySQL database. But so this is the metadata table, so 1 of 2. In the metadata reference table, we'll have 1 lake per row, its ID number, its name, and its source. So the source here is HydroWeb. And then you'll have the last column, which is the metadata, which is just stored as a dictionary. And the metadata will change from database to database. But generally includes kind of the similar information. So like location information, the temporal range of the collection, so when did they collect it? Sometimes they'll give you, like in this case, like the country and the status, but they're not standardized. And so we typically like to pick out some of the more generic metadata and then store all the rest of the specific database metadata kind of in its own dictionary that's still accessible. So we currently have around 2,200 lakes in here, which is up around 150 from January when we started it. That means 150 lakes have been added. So most estimates place global water bodies around like 1 billion, but you have to remember that most of those are pretty small, like little puddles, and not all of them are monitored. Their lake levels aren't all monitored. And so 2,200 is actually a pretty good swath of most large monitored lakes around the world, and especially in the US. Okay, so the other table we have is the lake water level table. And so this contains all the values for every lake in the database, which is about just under 9 million rows right now. It has the unique lake ID number, the date of the water level observation or measurement, the lake name. This is just the first alphabetical one, Aksaikin, it's in China. And then the actual water level value. These are in meters. There are still some USGS lakes I haven't been able to convert for weird reasons to meters, but pretty much all of them, again, this is prototype still, but pretty much all of them are in meters. The datums, I should say, are not quite standardized yet. That's another thing that's kind of on the list. But they do appear as they appear in the original database. So we just kind of pass all the data that the database gives us to the user, and we don't want to leave anything out. But that's a great first edition if anyone wants to work on it. So I'm just going to go over this simple kind of relational database logic, which is worth going over. So the tables, right, our metadata table and our lake water level table, they share this unique lake ID, right? So number 1 corresponds to number 1 here. And that allows us to link the metadata, right, with the kind of the water level values. And so that's kind of how the 2 tables talk to one another. And we're going to get into the actual like workflow here, but this is just kind of an overview. Is that you send an API to the API, or you'll send an HTTP request to the API Gateway, which then works with AWS Lambda to get the data, fetch this data from the database, and then sends it right back through to the end user. So we're going to go through how these things work now. Okay, so again, I had no experience with AWS before, so I'm sure a lot of people have experience here with it. But if you don't, trust me, it looks like really scary. But if you just like dive into the documentation for a couple of days, it's really well documented. So I'm probably preaching to the choir, but so API Gateway is essentially the AWS tool to build, define, and host APIs. Right, and so for our global lake level database, we use the REST protocol, which is pretty standard nowadays. It has 3 methods, which basically serve as one main method, which is this search method, right, which is just operates kind of as a GET request, and you can search with the lake ID, name, or source. And so that's going to come in when we talk about the LakePy search functions. And then the other 2 methods on the API are just kind of internal for getting data, and then one on its own for getting USGS date ranges, which was one of those creative coding solutions. But as you can see, there's no authorization, there's no API key required. And you might think that that's insecure, but I promise you it's not, and I'll tell you why. And why is because of AWS Lambda. So AWS Lambda is a little non-intuitive, or at least it was to me. Again, I had no experience, so it was really when they say run code without thinking about servers, I was kind of like, well, that's the only way I know how to run remote code. So it was kind of intimidating, but we'll walk through it. It's basically an on-demand compute service that lets you run code in response to certain events. One of those, which could be an HTTP request, right? And so this is what allows the API to basically pipe requests to the relational database. So AWS Lambda expects certain inputs, so we can say, okay, you have to have the request has to have lake ID, name, or source, and it definitely has to have lake ID. And then it queries the database automatically with those inputs, right? So this is different than someone being able to send an SQL query through the API and try and SQL inject it or something like that to try and drop all the rows or upload terabytes of data. Again, no one would really do this, but this is AWS's kind of best practices for security. And so in this way, we only allow one SQL command to ever happen, which is select. And that happens through Lambda. And if you don't provide kind of either a valid lake ID or name and source, then it will just refuse. So that's kind of how we deal with the security. But Lambda is interesting because if you've ever worked with Docker or packaging things, it kind of works like that. You have to upload a zipped file of both your code and all the dependencies that come with it. And it has to take a very specific form so that AWS knows kind of where to put the variables that come from the API into the functions in Lambda. So you can see this little kind of function down here, at least the very beginning. So I had to put PyMySQL as a dependency so that I could connect to the database from within Lambda and retrieve stuff from it. But again, this is so that people can't just go query the database, and it's always on demand without having to pay for server space. So AWS Lambda, highly recommend. It's kind of weird to get your head around at first, I would say, but it is very nice to just have something that spins up kind of on demand. And yeah, like they say, not think about servers. So I recommend that. So kind of here's the overall workflow. Now that we've kind of got all these parts, it starts with a simple search from LakePy, which we're about to go over, that gets converted to the proper HTTP GET request format, and then sent to the API endpoint. So when that happens, the Lambda functions kind of rise from their slumber like a dragon or something, and take the variables of interest from the REST API or the GET request, and they query the global lake level database with those specific variables in kind of this predefined SQL syntax, right? So there's just like a few pieces of information traveling from the end user through here, and then gets reformatted into an SQL query by Lambda, queries this, and then the Lambda function will return that data from the RDS in JSON format. Of course, that's piped through the API gateway back to the user. And then what LakePy will do will kind of decode that JSON and change it into a pandas data frame. or something easier to use. And so now we're going to talk more fully about the actual front end, which is the LakePy Python package. And this is what serves as the Python wrapper. So again, part of this is that we aim to make the LakePy package slick, like well documented. We wanted it to look nice, follow open source etiquette, and overall, I mean, above all, like work pretty well. So we didn't try to get like crafty or anything like that. We just wanted this to be easy to use as possible. So I'm not sure if speakers typically like fire up a Jupyter Hub server or something like that. I haven't done that. You know, if you want to follow along, you're more than welcome to. I can send the Jupyter file in the chat, but I'm going to be covering all of that stuff anyway. So if you need help doing that, we can like pause here. I just sent it in the chat. But if not, I'll go to the next slide, and like I said, I'll cover it.
Jake, are you going to attempt a live demo?
I can at the end. I just had some slides, but I mean, depending on how much time we have, I can totally give you a live demo.
Yeah, if you're comfortable doing that and we have time, that would be really neat.
Sure. Yeah. So let me walk you through some of this stuff quickly, and then we can do that. So I'll skip this. This is just the Jupyter overview. I'm trying to think of whether I should just do this live. Well, let's keep going with this. So to people familiar with object-oriented programming and popular Python packages like NumPy, Pandas, or SciPy, this stuff will look pretty familiar, right? So it's just importing it, and then we instantiate our Lake class by a search, right? So this is similar, again, if you use Pandas to kind of setting a DataFrame constructor equal to a variable, and then that variable kind of gets all these attributes and methods that get populated. So it's kind of similar. So we start our search off just by entering a name. I'm going to go for Lake Mead in Nevada. And so it will be as simple as this. You said Mead, this is my variable, equal to lk.search, and then I specify a name. And so if you do what I did and you don't specify the ID number, but you just want to search with words, right, that will pull everything that matches that in the database. So you see here we have HydroWeb gives us lake name, which is Mead, and then there's another one from the USGS, which is Mead Lake near Willard, Wisconsin. No offense to Willard, Wisconsin, but that is not what we want. So I'll redo the search, and then instead this time specify the ID number, which you can find right here. And so when only one lake is returned, it will populate that variable with all the metadata and the actual data itself, right? So a little table will pop out here, and it will tell us, okay, we have the lake name, all this metadata, the start date, end date, lat long. And these are all the things that come pre-configured with LakePy. So Lake Mead will have its name, its country, its continent, except not for HydroWeb lakes, the source, so the original database, its original unique ID from the database, our unique ID, the observation period, lat long, except for Gearon lakes. I'm working on that. Any miscellaneous data that is sent through, but we don't have use for right now. A time series of the water levels, and then the entire data frame from the database. And so you see, you just kind of do Mead.observation period, and it prints out a string. It's kind of the range of the data. You could do the same for lat long or the country or something like that. But something I really think is like part of the magic of LakePy is that, and something I really wanted to ensure is that the project comes out of the box immediately ready for visualization and analysis. So in fact, Mead.data, which is just this, is just a data frame. It's just a Pandas data frame with all its associated methods and everything like that. So you just see, I just did one line of code, and I said mead.data.waterlevel.describe, and we get descriptive statistics for the entire water level history, which is pretty nice. And then even things like plotting histograms of the water levels, it's just one line of code. I know this is with Seaborn, but I could have done this with the built-in Pandas methods just the same. And so that's what makes it really easy. It's like just 2 or 3 lines of code to like kind of query this and then start doing analysis on it. Okay, I just showed you that. And then we also have, right, the time series equivalent of this, which is nice. So the time series would just be Mead.timeSeries, and it would just be the date as the index as Pandas date time objects, and then the water level. So that makes it easy to kind of feed it into sort of some time series analysis stuff. Okay, so then there's two associated methods, right? So, oh, Siri came in. There's two associated methods, right? So a method in Python, right, is a function that's kind of attached to the class. So the first one we have is PlotMapView. It's a little experimental right now, but something I really had a lot of fun with. So it gets an overview of the area and uses this awesome little package called context.tile, which basically serves tile-based context maps through Python. So I will say right now the zoom levels are a little strange because we don't have shape files of the lakes. We just have one point in one dimension. The program can't figure out the optimal zoom level really well. But we're working on it, and at least it lets you check kind of whether you're in the right part of the world for your lake. And there's all these options like Open Topo or Esri Satellite, or even this Stamen watercolor map, which is like fun, but I don't think I'd use it academically. But you can do it. Okay. And then I think the final method that we'll talk about is the most helpful. So this is PlotTimeSeries. And it basically just does that for you, right? It does what it says. It just plots the time series, and it takes one line of code. The default plotting engine is Plotly, so we'll just open up a browser window and have this layout where you can adjust the time range. You can scroll this bar down here. I mean, it looks very good, and it was not hard on my end. It was the awesome Plotly plotting package, but that's what we can do. Then, if you're more familiar with something like Seaborn, you can just specify a Seaborn flag, which I should have put up in the title, but you can just specify the Seaborn flag and it comes out like that. Same thing with matplotlib. And then even better, you can tell it to return the plotting axis to you, so you can do your own kind of customized plotting. So future work, I'd like to really think about a QGIS plugin for this. I think it would line up with the open source nature of the project. Of course, that's in the future. I'm working on it. So maybe it will come hopefully in the near future. But talking about that, I want to talk about the state of the project and contributing. So if you or anyone else wants more work on their plate for no money, you should really think about contributing to LakePy. There are a bunch of things to do, like standardizing vertical datums, adding like a database intake protocol, more implementations that work with SciPy or NumPy or something like that, and even a command line interface. I mean, there's a lot of different ways this could go. This is hopefully just like kind of the starting off point, and hopefully we'll try to build some sort of open source community around it. And then finally, the project's still up and running, but as of right now, I'm funding it myself. ESIP has generously offered to help me out for up to a year, and so we're looking to do that. But we are looking for a kind of a long-term solution for building and maintaining the package. I'm working with possibly bringing it into the IU admins group. But if anyone has like ideas, grants, stuff to apply for, I mean, I'm here for it. So yeah, totally. We can either go to questions now. I can do a simple kind of live demo. It's kind of up to that, but I just want to acknowledge my funding source, which are Science Information Partners Winter 2020 grant, specifically Annie Burgess and Megan Carter, who's here. My collaborator, John Franey, I'd like to thank Derek for being so nice and helping me out with this talk, and then the AWS staff and all of y'all. So yeah, thanks. And then I can do questions or demo or what have you.
Jake, you're doing great on time. So we're
Cool.
only at the bottom of the hour. And so certainly from my perspective, I'd love to see sort of the demo. And then I think a lot of other people might be interested in grabbing the code that you have and trying it themselves.
Yeah, so let me get this rocking. Yeah, that's funny. My presenting time said 40 minutes, but it looks like it's only been like 35. All right. So first, I'll just kind of show you, if we have a little bit of time. So here's the GitHub page. You can see everything happened in January. I haven't worked on it as much as I'd like to in the past few months, but forgive me, I was writing a master's thesis. And so, yeah, this is what it looks like. We thankfully have a DOI. Annie Burgess at ESIP helped me do that. So it is citable, which is good. It kind of gives you an overview of the software used, kind of a quick start. Again, we wanted to make sure it was pretty well documented. Here's contribution guidelines and credits and stuff like that. But if you go into notebooks, there's just one lonely notebook in here right now, but more to come. And this is the LakePy walkthrough. So this is some of sort of the stuff that we saw. But so it really is simple as just import LakePy as LK. We can try another lake here. If anyone has one that they like particularly, you can shout it out, or I'll just pick one. I usually like some of the lakes in Texas are named really hilariously, like Lake Ray Hubbard, which I drove past on my way up here. Right. Okay. So when you search that, like here, what comes up is we have several things, right? So Lake Ray Hubbard near Forney, Ray Roberts Lake, which is close, but you know, no cigar. And then Hubbard Creek Reservoir near Breckenridge, Texas. Funny, they're all in Texas. But this is the one we're after, near Forney, which I've been to. Forney's a good place. And so now this is set right to our variable RH. Okay. So, or sorry. So it gave us 3 results, and then it tells us with a runtime warning, Ray Hubbard has more than one result, showing the 3 most relevant results, right? And so then what we would do is I would just copy this. Of course, this search process can probably be optimized, but we just literally replace the ID number. I'll change this variable for ease, right? You run it, okay, and then it spits this out, right? So we have our ID number, the name, the source, and then this is all the metadata that the USGS pipes through. So down to like, I mean, this is why I love the NWIS. It's just so much data. So anything from, you know, the vertical datums to the coordinate method, map scales, what have you. So you can use all of that if you use that or would like to. But for us, we can just look at some some typical metadata things like I was talking about. You even just have the So you even just have like this same metadata that you can pull out at any time. We could do our observation period. I keep doing that. It's so funny. My heart drops every time. I'm like, oh, it's not working. And so this is our observation period, only about, it's about 21 years or something like that. Right, we can get our lat longs. Oh my gosh, can you believe I keep doing that? We can get our lat longs, stuff like that. I mean, okay, so this is all the metadata, right? Let's try our PlotMapView. I pray God it works well like I want it to, and there it didn't. So yeah, so this is our still our kind of experimental version, unfortunately. Some of the USGS lakes will give you some trouble sometime, I think, because their projected coordinate system that the data is taken in is a little different, but that's okay. Oh, you know what it is? It's because I'm in a different environment. But okay, regardless, we'll move on, and I'll show you the thing that's really, I think, the most useful, which is just running that, and then this guy pops up, right? So this is a little wonky now, but it goes all the way back. You can do this kind of dynamic data filtering and time filtering. You can kind of look at specified intervals. Right, and so I really like that. You could also, like we said, do it as this plot. I'm not going to change it just now, although I guess I could. So I took a rolling average here, it looks like. So again, all of these methods are just sitting inside of Pandas and are just like waiting to be used, kind of. Let's see. Oh. Oh, there we go. I knew it was hanging out somewhere. Right, and so, that just plots kind of simply with Seaborn. I plotted that rolling average pretty easily just by taking kind of the rolling argument with the Pandas data frame. You can change up the colors if you want. Like I said, you can kind of do anything with these. If you're kind of a Pandas whiz, there's a lot of built-in stuff for data analytics. But yeah, but currently this is kind of what we have. And yeah, 2,200 lakes in the database currently. Sometimes there's the random duplicate, which we're trying to work through still, but for the most part, I'd say they're unique lakes. Let's let's see, we can really search for anything. Right, so I think this is near me right now, right? So the USGS is great because it has like every single lake in the US. So our global coverage is good, but the US coverage because of the USGS is just phenomenal, which is awesome. Yeah, and so you can just, oh, I specified the wrong ID number, but you can just kind of do the same thing, right? And so this kind of gives you an ability, which is something I needed, which is to look through this data like really quickly and easily. And so you see here, we have the lake name from the USGS and all their water levels and date timestamps. Maybe this one will work here. I'll write down it, yeah. So yeah, so that's kind of what it is. The documentation resides kind of in this S3 bucket. So feel free to kind of look at that, although it's kind of similar to what's on the GitHub. Yeah, you know, other than that, sometimes I'd like to say that something I do, y'all can't see that. Just do one quickly share. Okay, so something I do is I have this little drop-down terminal, and I'll always just do like import LakePy or I do Python. You know, you can do it from anywhere, and it's really simple. It's import LakePy is okay. Lake equals lk.search equals whatever. Yeah, we'll do one right. And so I just get them back in the terminal. I'll just rerun that search and specify the ID. We can do a different one. 337. Okay. Yeah, and then just simply, it will take a little bit of time to read the lake level records from the database, especially if it's one of these USGS lakes that have just daily data going back for like 70 years or something like that. But look, it's already done. And then it's just, you know, as simple as like plot. So that will just go to our browser. There it is. So yeah, so that's kind of it. I'd love to take questions or anything.
All right, Megan, are you monitoring chat just to see if there's any questions in there? So, and anyone that has a question, raise your hand, send it in the chat, or just speak up. We have a reasonably sized group that you can just shout out a question that you might have for Jake.
So there are no questions in the chat, but it looks like Madison has a question.
Okay.
Hi. Yeah, thanks for the presentation. This is great. I'm curious, I missed the very beginning, so I'm not sure exactly what your affiliation is, but I was just wondering, how are you, like, how or if you're connected with USGS? And if not, if USGS is aware of it, well, clearly some of us are, like Derek.
That's right.
But like, is there any effort on the USGS side to like stay in touch with you and maybe help to spread the word like about that this exists, like as a means to help folks get lake data?
Yeah,
just thoughts on that.
Yeah, no, so for me, right, so the entree I had to this whole thing was through ESIP, and that's how I kind of got through to the USGS community, just because, you know, ESIP and USGS are so intertwined. And then Derek and I have been talking a little bit about, you know, kind of that longevity sort of thing. Here, let me plug in my computer. But for me, I went to UT undergrad and master's. I'm actually a sedimentologist and stratigrapher by training, but I like coding. And now I'm starting a PhD at Indiana University. So I have 5 years and obviously would love to remain in touch and stuff like that. So.
Madison, what do you think? You know, I've really, you know, kind of made a note to myself to keep in touch with Jake, make sure that we're hearing some of the questions that he has about our APIs that he's making use of. I'd like to continue with introductions. Do you? I'd like him to be more involved with the CDI community. Do you have any suggestions for Jake?
Well, so it's funny because I just had a meeting about this similar with some folks at CU Boulder who have been working on like an API wrapper for USGS stream stats. And, and we also are thinking about having on August 26th through the Community for Data Integration, a discussion about this topic, like how is USGS, like how or should we be embracing open source projects that are built to help others use our data more easily? Like how would we go about doing that? Because people are doing really great work and it'd be great to spread that around and share it. But I don't think we're really doing that. And I don't think we know even all of the work that's being done out there. So it'd be cool if we could get some effort together or make it easy for people to tell us, hey, I'm using your data, or I built this wrapper or something like that. So
some centralized sort of
some more discussions around it.
Yeah, no, I mean, that would be great. And you know, I mean, you guys all know this, but this space is so dynamic right now. It seems like you have everything from people that are, you know, interested, you know, they have a 9-to-5 or whatever, but they're kind of interested. And so they work on the projects, or you have graduate students all the way up to, you know, USGS people or even people at like AWS or something like that, right? So I totally hear you. It seems like everything's going crazy right now in the geospatial coding. And I just really, for me, I'd really like to stay into that. And I'd like to make LakePy more kind of compliant with open source geospatial stuff. So the API, I'd like to make it like stack compliant and stuff like that. Because I think that that's the way that you kind of get everyone on a similar page, at least like, you know, working with the architecture. But as far as like just a big Slack or something like that, that would also be cool. So,
well,
yeah,
and we threw around the idea of there's kind of a new up and coming project called PyOpenSci, similar to our OpenSci, where they'll review kind of software packages and things like that. And so we were thinking, you know, one idea was, well, what if folks like Jake, who developed this stuff, were willing to go through PyOpenSci and kind of go through that review, and then that would give USGS perhaps a little more comfort in saying, you know, putting it on a website or saying, you know, here's tools that use our data and like maybe help you out or something like that. So just
no, that makes a lot of sense. No, definitely, I'd love to stay in touch for sure.
Cool, thanks.
Madison, do you want to invite Jake perhaps to maybe a CDI monthly? Is that, do you think that would be something that would make for a presentation? I know we had someone who presented on our packages that were using USGS endpoints. You know, that's I think that came out of New York Water Science Center. But
yeah, so I mean, that might be a question for Leslie, who's also on the call.
Leslie.
Meeting. But I mean, Jake, if you wanted to come, it's more of an informal discussion in the software development cluster at the end of August. But if you're available, I could invite you to that. And you know,
hey, I'm down.
Use it as a use case or something to
sure. Great, awesome, thanks.
Leslie, did you want to say something? Oh, you chatted something.
Yes, I said we will see how to spread the word more about this. It's really cool to see.
Thanks,
that's great.
Is that
Megan?
David? Did you have a question?
Oh, there's some questions. Yep.
I just see a hand raised.
Yeah, there's another hand. Go ahead, David.
Hey, Jake, I missed the beginning, but this cool presentation. And just so in the water mission area and in terms of water resources, there's a lot of interest in reservoir operations and being able to predict lake levels and reservoir levels. And there's codes that you're probably familiar with, like WEEP and Riverware and ModSim and whatnot. So I don't know. I mean, just thinking of, there could be interest. I could get you connected to people in the WMA. I think Jordan Reed, who's in charge of our data science group, would be a good person. He's a lake science person who does modeling, AI, ML kinds of things. So that's one connection. But just are you familiar with any of those things like Weep and Riverware and those kinds of codes?
In passing, but only in passing. Yeah.
And then more personally, do you know what you're going to work on for your PhD, or is it still up in the air?
Yeah. So for my PhD, so I decided to move away from the strat kind of background. I love field work, but I like coding. I also like coding, and I think I like it a little more. So I'm kind of working with the Edmonds group, Doug Edmonds, who really has embraced, he's one of the only people I think that's really in the sedimentology community embraced big kind of large scale remote sensing data. And so I was, attracted to working with him on basically developing these sort of architectures, these packages and stuff like that, and then flipping them around to kind of do large scale, global analytics of stuff like stream avulsions or something like that, right? So, because all the data is out there. And so it's not super defined right now, but all this is that all the data is out there from NASA satellites that are basically LiDAR sweeping the Earth every day, to imagery, to all that stuff. And it has Earth science applications, obviously, and there's more out there. And the question is in the rivers communities. For me, it's more of the looking at alluvial ridge height or levee slopes or something like that to predict things like flooding or stuff like that. But it's utilizing some of this big data, so you're not going out to one river and saying, oh, we're making a, we're creating a theory based on like a few data points, which is kind of how it's happened in the past. And so kind of using this big data to investigate some of these sedimentologic principles. So I'll be around in this space for sure.
Yeah, there's a USGS remote sensing branch in the water mission area that like Jack Eggleston, and they have some areas of this as well as, remote sensing of water levels and things like that. And maybe, Leslie's a geomorphologist by training as well, so that she might not be a bad connection.
Yeah.
Leslie, but Katie Scallick in the water mission area has a similar background, and so those are some names of people you might want to connect to.
Down. Perfect.
Thank you.
Thanks so much. Yeah, thanks, Dave.
Eric, I'm not seeing any more questions in the chat at the moment.
Okay, I've got a question since we've got a couple minutes here. So you gave a cost on what this costs to run. Is most of that storage? Since I don't see you're spinning up EC2s, so it's not a whole lot of compute, right?
So a lot of it. So part of this, admittedly, could be that I'm not aware of the best way to optimize AWS processes for cost. So I'm sure you could knock that down a little bit. Last time I checked, I think the biggest stuff was like the VPC. And the RDS is kind of, and then the API Gateway, I think it's a decent amount of cost. So like it's about $100 a month or so. I was on the free tier for a while, which was like awesome. But they pulled the plug on me. So yeah, it's about $100. I'm sure it could be optimized down if someone that really knew their AWS looked at it. But for right now, I think the biggest cost is the virtual clouds.
Yeah, I think that's one thing that we can do is look for opportunities to get you hosted.
That would be awesome.
Okay.
Because I love it. I love this project. I know.
I mean, so my next question is how does a sedimentologist get into the realm of AWS serverless and lambdas? So that's really the burning question.
It's a good question
because I'm really curious. Where did you find the time?
Yeah. So thankfully, I as an undergrad, I did some work with a hydroecologist, this guy Michael Young at UT, who's a soil guy, and I got hooked up with him just because he needed a research person. And he basically said, "Hey, I'll pay you to work for the summer, but you have to learn Python." And he was like, "I don't know it that well," but he's like, "I make everyone learn it because you have to." And that was like the best thing to ever happen to me. And so what this data was, I mean, it's published now, but it was basically 65 million shrubs that they cataloged with LiDAR and hyperspectral imagery. And it was trying to do kind of like a big kind of distribution analysis of all these shrubs. And so I got thrown into basically, you know, loading shapefiles into Arc GIS that had, you know, 65 million rows. It would crash all the time. So I had to learn it through ArcPy. And then it was through that vein of like having this like pain in the ass data that I had to load all the time. And I was just like, there's a better way to do this. And so stuff on the side. And then when I saw the ESIP, the request for funding, I had been thinking about this, and I'd been doing my own code, just kind of in Python. Like I'd like to keep my Python chops up. So I was doing stuff, and then I was like, okay, I think I could do this. And then the ESIP's which really kind of turned me into a full-fledged, like I use GitHub and PyCharm and like, you know, like an actual quote unquote coder. So that's kind of how I got into it. And my master's advisors were thankfully super okay with me spending half my time on coding, and they were like, what is this? Like, I don't know what it is, but you got money for it, like good job, keep going. So they were pretty hands off and let me do it. So that's kind of how I got into it. And then I wanted to make sure in my PhD I could keep coding for sure.
Okay.
Yeah,
oh, that's fantastic. Yeah, so I think you've seen that there's an interest in what you're doing, certainly from the USGS side. So let's do everything that we can to keep in touch. I think Madison's going to reach out, perhaps Leslie. I'm certainly going to look for opportunities for us to interact with you. And
great.
Again, I really appreciate, well, ESIP first for funding, Jake for providing this wonderful presentation. And yeah, and then to all of you who took time out of your day to attend this presentation, thanks for coming.
Yeah, thanks everyone.
We will see you all in another month.